All right, guys, so this next video is talking about applying Le Chatelier's principle, meaning like why is Le Chatelier's principle important, and like just what can it help us figure out, I guess, or do. So first, we want to talk about the common ion effect. So it occurs in aqueous solutions. So we have a diagram here of AgNO3 dissolved in water. When a substance is added that shares the same ion, so it changes the concentration of that ion and causes a shift. So, what does that mean? When I dissolve an ionic compound in water, it breaks apart into ions. So, just underneath this beaker, I started off with AgNO3 solid, and when I put it in water, it breaks up into silver ions and NO3 ions. So that's what I have going on in this container. Now, if this was a saturated solution, I'd have some undissolved AgNO3 at the bottom, and the rate of dissolving and the rate of crystallization would be equal to each other, right? So now it's saying, what will happen if I add any NO3 to this solution? So let's take a look at what happens to NaNO3 when I drop it into water. It breaks up into sodium ions and nitrate ions. So really what I'm doing is I'm taking the amount of NO3 ions. I'm going to change my color. Actually, you guys, we should have drawn a double arrow here because we were in equilibrium with a saturated solution. I'm going to change my color so that we can see this better. What I'm doing is I'm adding more NO3 ions to this solution because that's the ion that both of these solids had in common. So I'm taking NO3 and I'm increasing the concentration, which is considered stressful to a system in equilibrium. So the stress is going to be that I increased the concentration of the nitrate ion. So what is my reaction going to do? It's going to want to shift to get rid of the extra NO3 ions. And which way is it going to shift in order to do that? We're going to shift left. By going to the left, I'm turning more Ag and NO3 ions into AgNO3 solid. So I'm getting rid of some of those extra ions in solution. So I'm doing the opposite of the stress. So you have to think about what you're adding to a mixture that's already created. If it's got a similar ion in it than what's already dissolved, that's going to be considered a stress and it's going to mess up equilibrium. The other thing that we might want to think about is forcing a reaction to go to completion. So completion means that the reaction is favored very much so in one direction that the other direction can't keep up. You basically just form a whole bunch of product or whatever side you want really. And that's it. So if we think about this reaction here, this is called the Haber process and it makes ammonia. So let's say we want to only have ammonia as our yield. We just want to make a whole bunch of ammonia. We don't want this to be in equilibrium and ammonia turning back into nitrogen and hydrogen. So if you want to make ammonia, which way do we want the reaction to be going? Which direction is going to make more ammonia? Going to the right. So this is basically asking us how to shift right. And we have to come up with ways in order to do that. Okay. So I want you guys to think of some ways that you can make this reaction go to the right. Think about what we talked about in our last video. Can you change the temperature? Can you change the pressure? Can you change any of these concentrations? What will make it go right? And just to remind you, this is an exothermic reaction. So I'll put energy over on this side. And that should help you figure out some ways. Write down that list and we'll go over it tomorrow. Okay, Do catalysts affect equilibrium? So guys, I have a potential energy diagram here, and I want to remind you how a catalyst changes this diagram, right? Not only does it lower the activation energy of the forward reaction, but if I was going to go in reverse, the activation energy is also lowered. So if we're increasing the rate in both directions, is that going to mess up my equilibrium? Is that going to be considered a stress? No, not at all. They love to throw catalyst in there as what is a stress, and it's just not. Concentration, temperature, and pressure are. A way to think about this, guys, let's go back to our sports analogy. I think we talked about, I don't remember what sport we talked about. Let's talk about baseball, right? There's 9 players on the field, and let's say there's 20 players on the bench, right? So let's say the pitcher is going to get pulled out because he's starting to stink, right? So if the pitcher comes off, one person leaves the field, another person goes back on the field to replace them. That's equilibrium, right? A catalyst would be like if the pitcher ran off the field instead of walked off the field. Well, if the person replacing him ran onto the field instead of walking onto the field, they're still switching places at an equal rate. And that's considered a catalyst. They're both running instead of both walking. So everything stays the same. All right. Irreversible reactions or reactions that go to completion. So basically, if you have a KEQ, an equilibrium constant, that's very, very large or small, that's saying that that reaction is probably irreversible or it went to completion. It went to one side much more than the other side, and we really can't say it's in equilibrium. So if the KEQ is very large, that means it went in the forward direction. The products are greater. If it's a very small one, then the reverse reaction was favored. But you guys can figure that out because you know that formula. So an example of this is rusting. So if you have iron, right, and you leave it outside and you expose it to air and you expose it to moisture, that iron reacts with oxygen in the air and it turns into rust. Now, this equation is not balanced. I just want you guys to know, I know that. Now, the KEQ for this equation is 10 to the 11th power. It's a huge number, which means when I did products divided by reactants, my products were much greater than my reactants. And if you think about this, guys, just think about life. If you have furniture outside or you left your bike outside or even on some cars, if the paint chips, right? If metal rusts, it doesn't like sit there and then all of a sudden become unrusted. This is not a chemical reaction that typically we see going in reverse, right? So we can say that this is irreversible or goes to completion. It makes rust. Once all the iron turns into rust, the reaction completely stops. Okay, so that is it for applications, and we will talk tomorrow.